Sam, hope you're feeling better. All right, so plan for today looks like this. First thing I wanted to do, I wanted to review some of the types of reactions, things that we started talking about back on Friday, just to make sure we have those things down, how we can identify what type of reaction something is just by looking at it. Second thing, I wanted to review the acids and bases stuff you were supposed to fill out last night in the outlines. I want to just make sure we review that, make sure we got the basics down, and then hopefully we'll get to the rates of reaction, which was the new sheet that I gave you today over on the red tray, and then we'll go from there. As far as calendar goes, tomorrow you guys are in lab, and we'll talk about types of chemical reactions lab. It's a real lab with like chemicals and fire, and there's even a little, I mean, an explosion is probably an overstatement of what's going to happen, but there is a, a loud noise,
What's the percentage of us dying?
Small. A very small percentage of you dying. The percentage, I mean, like very small, very small. The percentage of you catching a disease would be no higher than percentage of you catching a disease in this room any other day. So, yeah.
How about burning ourselves?
No, I mean, there's fire, so. Yes.
I saw this in a book today that humans are more scared of talking in front of people than dying.
Yes, it's very true. Actually, Sam, a little unrelated conversation for you. At the beginning of the year, Time Magazine did a little an edition. It was called 2012 User's Guide, and there was like all these things that blah blah. So, and they had a little chart that it was like an x-axis and a y-axis, and the one axis was how afraid we are of stuff, and then the other axis was how dangerous it actually is. And like one of the most things that we're afraid of is flying, like a lot of, but it's like one of the most safe activities that you can do. You're actually more likely to die in a crash on the way to the airport than you are to die in a plane crash. Yeah, there's more cars, you drive more miles, and things like that. What? Yeah, but a lot of people are really afraid of that. Spiders is like another thing. Like spiders, a lot of people are very, very afraid of spiders, but they eat other bugs. That's what spiders do. They don't really attack humans, right? Every once in a while, But they said that one of the things that we are so very not worried about, but is really, really dangerous, is obesity. Like the health risks that come from weight issues and things like that are far more dangerous than flying. But people are like, man, they don't worry about that kind of stuff. So. On TLC. My sister. TLC is just.
You're talking about if you're one leg or being very sensitive.
I honestly, my last comment on Say Yes to the Dress, my wife watches Say Yes to the Dress. I honestly really,
It's so stupid.
But when those girls come out in the different dresses, I can't I can tell it's a different dress, but I'm like, she looks really good in that. She doesn't look good in that. Like what? It looks like you in a wedding dress. That's what it looks like to me. I don't know.
You never see where they pick up wedding dresses.
Yeah, it's like
a TV show. It's really funny in the Real Housewives.
It's such a moving moment when a bride finds her dress.
Really?
They all end up crying pretty much. So.
Yeah, it's in like red. Okay, so when you're on a plane, is it possible to like go?
Yeah, you can go next to another plane, but they try to keep them apart.
So like if you're on a plane and like there's a plane coming by, you can like see the person.
Technically you can be close enough,
The wings would.
Technically you can be close enough, but they try to avoid getting planes that close to one another just in case.
So wait, people are more scared of talking to people than dying.
That if you ask people like what they're more afraid of, people would probably say like, quite honestly.
I would say.
At this point in time, are you really worried about dying? Most of you probably are. So,
I've had some.
you may have.
Sharks and
All right, let's go. So, Wednesday. Hey, come on. We're already behind from yesterday. Hey, We're already behind up with yesterday's conversation. We need to get as far as tomorrow goes. As far as tomorrow goes, we are in lab. We might have to finish up some rates of reaction stuff depending on how far we get today and how far we don't get today. So we may squeeze that in at the beginning. Right now, we are still on track for quiz tomorrow, but if we don't get through the rates of reaction stuff today in class, I might push that quiz to Friday at the beginning of the period. Don't forget that tomorrow's lab is the lab that you will be writing your formal lab report off of for this grading period. So Friday in class, we'll have time to work on that. I mentioned to you last week, and I'll mention to you again now and tomorrow as well, there is no library time reserved for you guys on Friday. The library was already full during third period when I requested it, which was like 2.5 weeks ago. It was already full, so sorry about that. But if you have something, like if you have the laptop or something that you want to bring in so you can work on your stuff in here, that's fine. If not, you can just work on it in class and, you know, write things down, type it up when you get home, whatever. Okay? Good? All right. Lab report due next Tuesday. So you'll have Friday in class to work on it. If you want to bring it back on Monday, ask me questions. Fix it on Monday night. Bring it in for Tuesday. Good there? All right. Wrapping up yesterday's conversation, I think I mentioned to you guys at the end of the period. If I didn't, I will now. In the meeting that you guys went to yesterday, they may have mentioned Friday being like teacher signature day or something like that, recommendation day. Okay. Because we spent yesterday in class devoted to questions and looking at different things, stuff like that, I won't take Friday to set aside just to do signatures. You're not actually scheduling classes for another couple of weeks, like, you know, meeting with your counselor and stuff like that. So sometime between now and 2 weeks from now, all right, see me before class, after class, study hall, lunch, something like that, and we can discuss stuff for next year, or I can just sign your sheet or whatever. But is that good? See me sometime on your own. All right. Let's start here. Last Friday, we talked about types of chemical reactions, and we said that if we look at all the chemical reactions that occur out there in nature, they all fall into like 5 categories. So the first category we talked about was combustion. What do we need to have in order for something to be a combustion reaction? How do we know it's a combustion reaction? Here's the cut. 2 oxygens where? Which part of the equation? The reactants, right? So if we get this, right? Fe2O3, that's a combustion reaction. Why? Because it's got this. Because it's got this. O2 in the reactant side. Okay? We spent a good amount of time talking about a specific type of combustion reaction, and that was the combustion reaction of hydrocarbons. This compound is a hydrocarbon. Why? What is it made out of?
Carbon and hydrogen.
Carbon and hydrogen. When it reacts with oxygen in a combustion reaction. Why is this a combustion reaction? Because it's got oxygen in the reactant side. Okay? It always forms 2 products. And what did we say those 2 products were? Water and carbon dioxide. CO2, H2O. That does not mean that every combustion reaction has these 2 products. Okay? This is a combustion reaction, and it doesn't have those 2 products. This is a combustion reaction, and it does. Only the combustion of hydrocarbons will produce these 2 products. Lauren, go ahead.
So why does oxygen get in the product?
This is not, sorry, Lauren, this is not balanced. Okay, yeah, so if we balanced it, it would look like this. Okay, but that still counts as a combustion reaction because remember, adding this 3 coefficient in front of oxygen, it doesn't change what oxygen is, it just changes how much oxygen is there. Okay, so yeah, it's still a combustion reaction. Are we getting a combustion reaction?
Yeah.
Okay. The other 4, there's an analogy that we can sort of look at to describe the general format of those equations, see how they sort of relate to one another. So the first type of reaction that we talked about was called a synthesis reaction. And because you know English, we talked about that a synthesis reaction is what are we doing in a synthesis reaction?
Small things and putting them together.
Taking small things, putting them together to make big things. When we look at the general form for a combustion reaction, it looks something like this, right? A plus B equals AB. If we were looking at an equation, a chemical equation, the AB, let me do this. If we're looking at a chemical equation for a synthesis reaction, what would the A and the B represent separately like that? What might we be looking for in an equation? Two elements, right? So element plus element is giving us what, Allison? A compound. So element plus element gives a compound, right? Element plus element gives us compound. Now, we could also look for small compound plus small compound gives us bigger compound. Both of those would be synthesis reactions because we're putting things together, right? Good there?
Yeah.
Sometimes, in order to see how they relate to one another, we use the example of the chemical dance. Not as in a dance move, okay, but in like an event, like the chemical winter formal. Okay? So, as far as the chemical winter formal goes, what does a synthesis reaction represent? What has happened at this said winter formal here? Penny,
Guy meets girl and dance.
did they come together?
Yes.
No.
No, they came separately.
They came separately to the dance, but they met at the dance. Maybe a Taylor Swift song is on. Who knows, right?
Definitely
Yeah, we'll cut it.
a slow dance.
Yeah, no, Adele's the next one. So, all right. Anyway, so this is, right, two people come to the dance together, or sorry, separately. They meet at the dance, happily ever after. It's a love story, right? Okay. So anyway, just so you know, it all goes downhill from here, right? So this is the high point of the chemical winter formal, by the way. So 6 months later, right, at chemical homecomings next year, okay, A and B elements that created their compound, right? It's just not working anymore. It's not a stable situation anymore. Okay? It's a high energy situation. And so this beautiful couple that formed at chemical winter formal now goes through decomposition. All right. So I know, so
Someone like you.
downer. So there's our general form. Yeah, like I said, this is more like a Adele song. So
Got it.
all right. So
Roll in the deep.
yeah. So general form. Actually, rolling in deep is a little bit more of the next one. Actually,
Okay.
so all right. So
I could have had it all.
yeah. So actually, the next one is more like rumor has it. Actually. But anyway, so here.
You should know.
Don't you gotta listen to the radio? I happen to like Adele, thank you. So, anyway, decomposition. General form looks like this, right? If we're looking at an equation, what does this represent? What would we be looking for in an equation? Allison?
It would be the compound.
We start with a compound on the reactant side
And we split apart into
into two elements. Or we start with a big compound,
and
two smaller compounds. Okay? Are we good on decomposition?
Yes.
Okay. Next. Single replacement reaction. Okay. There's the general form for our single replacement reaction. Right? Let's go over the equation first. What are we going to see in the reactants of our equation? A compound and an element. Okay? This is the element, right? This is the compound. Okay? What are we going to see in the products of that equation? Another element, a different element than we started with, and then a different compound than we started with. Okay? Awesome, go ahead.
Why isn't it goes to C plus AD?
That is kind of here. Actually, let me do this. Yep. So if we look, Allison, at this. Okay. So in the first equation, right, we start off with this compound, which is the AgNO3, okay, silver nitrate. Then copper is the element that we start with, right? So copper is a metal. It's going to go in and replace the metal in this compound, right? So it goes in and kicks the silver out, and the silver is left there by itself, okay? But in the second one, right, here's the compound, the potassium iodide, but here is the element, the chlorine by itself. Chlorine's going to go in and kick out the iodide. Does that make sense? So it really depends. So if it kicks out the back of that compound, right, to form an element with the, with the front. Because chlorine is more of an anion, so it replaces the anion in this compound, right? This is, a guy who goes in and steals the girl. This is a girl who goes in and steals the guy. Right?
Is the guy back?
No, same guy. See, chlorine is, you know what this is? This is you belong to me, right? So. Like,
I'm not feeling it. I don't know what it's on.
Right? Taylor Swift, you belong to me. It's like, you know. You belong with me.
Thanks, Chuck. He got it with you. This could be like.
Yeah, that one. Right?
You're on the phone.
Because like, like what is nitrate doing with silver? Totally see with copper. Silver doesn't know you like I do, right?
That's what you kicks him out.
So yeah, right? I mean, at the end of the song, right? Isn't that what happens? I mean, if you see the video, isn't that what happens? Please.
What is fair question?
How old do you think I am? Like I don't just go home and watch the news and go to bed at 7 o'clock. Right?
I didn't think you were like you're bold. You're you're a guy.
Oh my god. This on an unrelated note, and this will be out there like on the record because I'm recording this, right? I mean when that Taylor Swift song comes on, right? Whatever. I gotta listen all the way to the end. Right? Not because I really like it, just because it's so damn catchy. And not turn it off. I can't turn it off. Why? Why can't I turn this off? So, anyway. So, yeah, go home and watch this.
I'm playing it.
So, are we good? Post Taylor Swift discussion. Are we good with the single replacement? Okay. So, the last one, which could spur a lot of discussion, which we'll sort of table for another time, right? So.
It's like promiscuous, right?
Well, see, I mean, you gotta start with like two couples,
Okay,
and then,
never mind.
so,
Diverge.
anyway, yes. So, I mean, I'm sure there's some movie that relates to this.
The holiday.
Is it the holiday? I don't know.
Show White Swap.
It's very wife swappy.
No, I
Yes.
think it's holiday.
Good. Anyway,
So.
so, okay. So, Alice,
No, not wait.
Alice, seeing as how you've been rolling with this for us, okay? If we're looking at the chemical equation, what are we looking for in this type of reaction? What would an equation?
There's two elements. There's two compounds.
There's two compounds, and then they end up forming
Another two compounds.
another two compounds, but they're different compounds, right? We're trading cations and anions here, right? As an example, okay, go here. I'll bring up this one because you're going to see it tomorrow. Okay? Potassium iodide, Ki, lead nitrate, two compounds, right? But then they end up forming this new compound. The beginning of it is potassium, right? Potassium started off attached to the iodine, but now it's attached to the nitrate, which was the anion in this compound originally, right? Then it ends up also forming lead iodide, lead which was the front of this compound and the back of this compound. So it's compound plus compound equals compound plus compound, but there are two new compounds that get formed.
So that would be an example of double
Double replacement. Yep. Go ahead.
On the homework a few nights ago, there's this question. It said, what are the 3 results of
Yeah, I'm not really sure about that one, so disregard that question. So, I'm not sure what they were looking for there. I mean, I can look it up in the book, but off the top of my head, the answer to that question doesn't seem obvious.
Okay.
Nikki, okay?
If the NO3 in the reaction
Yep.
side, that didn't have the 2, if there wasn't a 2, would it react with the potassium?
Well, okay, so, yeah, the 2 just comes from it has to balance out the lead.
Yeah, but if it didn't have the 2, though, would it?
If it didn't have the 2, it wouldn't form this compound originally. That's how it has to form this compound originally.
Is that 2 of the PB3?
No. So, actually, Kenny, that's a good question, right? This 2, right here, hey, so, we are recording this, right? This 2 only applies to the stuff inside the parentheses, right? The 2 outside the parentheses only applies to the stuff inside the parentheses. If we do this, right, if we put the coefficient out in front, that would apply to everything, right? If we change the formula so it looked like this, now that 2 only applies to the lead, but not to the stuff inside.
So is NO 6.
How many N's are in this formula? 1. No. It is.
Oh.
2 N's, 6 O's.
Oh, because the 2 would go.
It goes to everything. Miriam, go ahead.
Do you have to know, like, why they would replace it?
No, it all has to do with energy. These 2, Miriam, these 2 compounds here are more stable than these 2 compounds were to begin with.
Okay, so
If we mix these 2 compounds together, this one and this one, nothing would happen because these are more stable than these 2. So it doesn't automatically happen. It has to do with an energy. Which ones are more stable?
okay, so we just need to know, like, that would be double replacement.
Yeah. If you saw this, this would be a double replacement.
Okay.
All right, we good here? Yeah. Okay. Let's go here next. Yesterday, this was your open screen, which you never saw because we were discussing.
Listen to Taylor Swift.
So,
Why does it say, what am I going to do?
I mean, other than listen to Taylor Swift, obviously. So, yes, Allison.
Okay, and also, is it another difference, like in a single replacement and double replacement? Like when we're looking at the ABC thing, doesn't single replacement have an element, like have elements, and double replacement only has compound?
Right. Like we said, if we're looking at, for a double replacement reaction, it's compound plus compound equals compound plus compound. For a single replacement reaction, it's element plus compound equals element plus compound.
Yeah, but in double, it's like compound.
Compound, 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 compound. All right. Here was the list of objectives that we were supposed to cover yesterday in class. Okay. This is what I asked you guys to look at last night by filling out the outline. So, first, acid. There's one formula or one thing we're looking for in order for something to be considered an acid. What is that one thing? Allison, go ahead. Okay. For acids, we are looking for this. Okay? We refer to this as the hydronium ion. Okay? If you dissolve something in water and it ends up giving you this, we consider that substance an acid. Okay? That's the key to acidity. Okay?
How do you know that you get that?
You can tell by looking at the formula, all right? So I believe the one example that they gave you that was in the notes was this one, right?
Yep.
HCl plus H2O, and when you dissolve that, you get H3O plus and Cl minus, right? Generally, you're going to see things that have hydrogen out in front of them are going to be acids, okay? So if we're looking at things like this, or red, things like this, or things like this, notice that they all have the hydrogen out in front. That's what we generally look for to see if something's going to be an acid when we dissolve it in water. Okay? Chris, go ahead. it's trading electrons and stuff like that.
So it's like representing anions.
Yes, representing anion, cation, basically, yeah. So that when we dissolve it in water, not that you need to know the process of this, but when we dissolve this compound in water, the HCl, which by itself is a gas, okay, when we dissolve it in water, it forms these two ions.
It's always going to form those two.
Yeah, and that's what makes it an acid. Why does that happen? It all comes back to energy. These two things separate in this format with the plus and the minus are more stable than these two things balanced out charge-wise.
So the one below it would be, if you add H2O, it would produce H3O plus F.
Yep.
Okay, what?
Don't worry about it. Like I said, you don't need to know why, just know that it does. Yeah. Go ahead.
Which part of the formula is the acid? Is the HCl the acid or the final?
Technically, things will become acid when we dissolve them in water. HCl by itself is not an acid, it's hydrogen chloride. It's actually a gas. But when we dissolve that gas in water, it forms the hydronium ions, the H3O+, and that's what it now is an acid. The solution of hydrogen chloride is an acid, not the hydrogen chloride itself. Does that make sense? Okay. On the other hand, we talk about bases. What's the formula that's important for the base? Nelson? The hydroxide ion, right? The OH minus, which is hydroxide. If we dissolve something in water and it produces hydroxide ions, we consider that substance a base. So Allison, if we're looking at a formula, we look for the OH for something like this, right? NaOH, like that. When we dissolve it in water, it splits up into Na plus and OH minus. It's not quite as easy to follow as the acid one is, but that's okay. Allison, go ahead.
Wait, so to find out that it's like a base or an acid, you have to look for those like two?
Yep. Does it have hydrogen at the front of it? If it does, it's probably an acid. If it has an OH, what?
If it doesn't and it has H3O plus, is it still an acid or it has to have hydrogen?
Yeah,
at the front?
but Allison, before we dissolve it in water, you're going to see generally that it has the hydrogen at the beginning of the compound. That's an indicator that when you dissolve it in water, it's going to form the H3O plus. Because you need the water to get the H3O plus, right? But you need that extra hydrogen from the compound. Okay? Bases, on the other hand, hydroxide. So you look for the OH at the end. Okay? Chris, go ahead.
You read another one besides like
If we had something like this, calcium hydroxide, okay, it would split up into a calcium, but calcium has a +2, right? And then it would end up as two OHs like that, because they all end up separate. Say again?
Why would it be +2 because of that?
Where is calcium on the periodic table?
Oh, it's not this metal.
Alkali earth metal, right? Right? It has to use the 2. That's why it ends up with calcium +2 oxide. All right, we get there. General properties. Acids. What do we look at when something is an acid? What are some of the general properties? Sour. Okay. It reacts with metals to produce hydrogen.
Which is blue or red.
Yeah, generally blue to red. Although, depending on if you have litmus or pH paper, it can do different things. But anyway, it produces certain color changes. On the other hand, the bases. Bitter taste. Generally, they have that kind of a slippery feel like soap.
Color
Then
change.
different color changes than the acids produce. Okay. All right. Next. Yes, Allison.
What does it mean when it says produces certain changes indicators including litmus to red?
Bases will turn a substance that's called blue litmus and make it turn red within a certain solution. Okay. Allison, do you know what hydrangeas are? They're flowers. Okay. They're a type of flowers that they're kind of a big poofy flower, but you can actually make them change their color depending on what you put in the soil what kind of, do you put an acid, do you put more acid stuff, do you put more basic stuff in the soil, you can actually get them to turn out to be pink or blue, depending on what you're doing, because there's a chemical in there that is it changes colors depending on the acidity that it's the situation. Next, pH scale. First, number-wise, what does our pH scale run from? 0 to 14. Okay. What does the pH scale measure for us? What is it telling us about, Chris?
The concentration of the hydronium ions.
Okay. The pH scale is telling you how many of these hydronium ions are there in the solution. Okay. The part that gets a little tricky, the more H3O plus ions you have, what happens to the pH value? It goes down, right? So if you increase the H3O plus, the pH value actually goes down. Okay? 7 being in the middle. 7 is completely neutral. It's not an acid or a base. Completely in the middle. Do we know what has a pH of 7? Pure water. Okay? Water is neither acidic nor basic. Okay? Completely in the middle. It's sour, but it doesn't. Sour Patch Kids have a lot of acidity in it. It's basically citric acid. Okay?
Warheads,
Blueberries are a little acidic, yeah, because they have that. Most fruits are a little acidic.
You know the candy, the warheads, how like you can taste.
That's why they are bad for your teeth. Yeah, that's why. Bananas are pretty neutral.
You know the warhead things, like sour candies.
Yeah, All right. So the lower the pH value, the more acidic something is. The higher the pH value, the more basic it is. Okay. Are we good there? All right. Last thing that we talk about are neutralization reactions. So here first. So, neutralization reaction. Neutralization reaction is a double replacement reaction, meaning compound plus compound gives us compound plus compound. It's a double replacement reaction between an acid and a base. When you have a double replacement reaction between an acid and base, you always end up with 2 products. One is water. The other one is an ionic compound that we call a salt. Okay? Salt is a general term that we use for an ionic compound. So, real quick, right? If we look here, come on. There we go. If we start off with this reaction, compound plus compound, okay? Also, if we're looking at these 2 formulas, right? There's the H out in front of this one, so that's telling you acid. There's the OH in the back of that one, that's telling you base. Okay? Double replacement. Double replacement. We flip the fronts to the backs, right? So if we take the front of this one and join it together with the back of this one, we end up with this, right? What is this? Water. H-O-H, H2O. Say again? You could write it as H2O. Niraj, the reason why we usually write it this way, like when we're introducing this concept, is so you can follow the OH group. You know what I'm saying?
Got it.
It started attached here, now it's attached here. Yes, because what kind of an element is Cl? Non-metals, so we break up in a second. Alright, hey, I know the bell just rang. Fill out the reaction rates outline. We'll talk about it at the beginning of class tomorrow. No, it's Friday. Fill out the reaction rates outline.
So, I asked my mom,